Attached to objects for identification, tags are actively used in many industries, like shipping, retail, robotics, and manufacturing. With augmented reality getting more popular, wearable devices promise to enrich our daily interactions by providing information to us whenever we need it. These devices need to constantly identify what is around us and display related digital content. Just as an example, imagine that you're at a store browsing different items. You want to get further information about a product, the unit price, calorie information, or cheaper alternatives. For this to work, the objects around us need to carry labels that describe what they are and communicate this information to digital devices. While QR codes are great for this purpose, it is just not plausible to slap a barcode on everything around us. I envision that one day, every physical object in our lives will contain an integrated fingerprint that will give us information about the object. And we will be able to access this just by pointing our devices at the objects. This is familiar to us in the digital ecosystem, where audio or image files include metadata embedded in them that helps the user seamlessly identify and get information about them. I'm planning to transfer this paradigm to physical objects using physical unobtrusive tags. So I achieved this HCI mission using novel techniques in digital fabrication, imaging, and computer vision to create two types of unobtrusive tags, natural tags and engineered tags. Today, I will be talking about different projects that fall into these two categories. Let's talk about natural tags first. So these allow us to leverage objects' natural properties as an ID, such as their microns, scale, surface texture. And as an example, I would like to talk about my recent project, SensiCut, a material sensing platform for laser cutters using speckle imaging and deep learning. So here's a question for everyone. What materials do you see here? They all look similar, but are they the same type? So they're actually completely different materials, as you see below. And SensiCut can actually sense and distinguish between these different material types and then set the correct laser power and speed values for cutting or engraving them. Or even warn the user if the chosen material is actually hazardous for laser cutting. To clarify my motivation, let me start by explaining the common laser cutting workflow today. So when a user wants to laser cut a design, they first select the material from stockpiles in a shared workshop, such as this one in our lab, where postdoc Isabel is looking for a piece of extruded acrylic. So as you see, these materials are often left unlabeled, which you might have experienced, or they may be hard to distinguish because they look similar. So after picking a sheet, you would then launch laser cutter software and hopefully make an educated guess and select the right material from a big database. And if you choose the correct one, that's great. But in reality, it's tough to get it right the first time, especially if you're a novice. So what happens when it goes wrong, right? So the best case scenario is you haven't applied enough laser power, so the outline is not cut through. So you have to like put it back and try to apply the laser once again and hope that it's aligned in the same position. Or more concerning, you may have chosen a material like PVC that is not intended for laser cutting because it releases toxic fumes when laser is applied to it. And perhaps the worst scenario, the laser power is too high and the workshop is set on fire, which it happened actually once. So as you can imagine, these possibilities not only raise the entry barrier to laser cutting for beginners, but also even for expert users, differentiating between visually similar workshop materials, which you see here, including those that are suitable or unsuitable for laser cutting, remains an obstacle. Thus, laser cutter users want smarter machines that can identify materials that they're working with, so that the system can suggest settings based on material, as shown in a KITE 2020 study. In SensiCut, our goal is to identify materials by leveraging their inherent features. We do this by using an optical method called laser speckle imaging, which helps us sense the surface's microstructure. Speckle imaging works by pointing a laser onto the material so that the laser interacts with the very tiny features of the surface, which you see at the bottom. When the light source is on, it emits the laser beam, marked green here, and these rays are reflected off the surface, arriving at the pixels of the image sensor on the top right. Now, phase differences between these rays cause mutual interference at each pixel, either destructive or constructive interference, which you see here as dark and bright pixels in the resulting 2D image. So when I was first experimenting with this technique, I took pictures like this one with a regular camera which has an optical lens. So we see that the green laser appears as a small dot on the surface. And here's a zoomed in version from the same setup, which shows the speckle pattern better. However, it is still present in only a small portion of the photo. This is because the lens of the camera directs not just the laser light, but all the available light rays in the environment onto the sensor. And this gives us less speckle data to work with. I noticed when you remove the lens from the camera, though, it is only the reflected laser light that lands on the image sensor. Thus, the resolution of the speckle is as large as the entire image, and this is a much clearer pattern to work with. And here you'll see this in action. The camera has no lens currently, so we see nothing on the display in regular lighting. But when you turn the laser pointer on, the speckles are visible clearly. So in short, the distribution in these patterns are distinct for each surface, and therefore lets us easily classify the material. To make this more clear, I actually went into a material science lab and used an electron microscope to get these micron scale images, which you see in the middle, so that we can really see how different these materials actually are on the nanoscale. So now that we know about this technology, I would like to talk about the UI we built for it and what kind of applications we use it for. As you know, there's a great demand for personal protective equipment these days. And in this example, my friend Jack quickly needs to fabricate a face shield for himself using the scrap materials in the workshop. So he downloads this open source file from the internet. And for the shield, he should use a flexible material, right? So he goes through the scraps, which were left unlabeled, but he picks a flexible one and places in the laser cutter. And after loading the cut file for the first part, he adjusts its position on the canvas and clicks the pinpoint button to make the laser cutter go to a point on the sheet. And SensiCut then takes a picture of the speckle pattern at this point, classifies it, and shows the result in the UI. So it turns out the material is polycarbonate, which SensiCut knows is hazardous for laser cutting. Therefore, Jack goes back to the scrap materials, chooses a different flexible plastic, and repeats the process. So this time the material is identified as acetate, which is a suitable plastic for the shield. Jack confirms this and enters the thickness value. And once confirmed, the system automatically retrieves the appropriate settings and starts cutting the sheet. Next, he repeats the procedure for the second part, which is the visor, as you see here. This time, the sensed material is acrylic, and once confirmed, the system automatically cuts the shapes with the right settings. Now all the parts are here, so Jack can assemble the face shield. Ta-da! I also want to show you another application very common among laser cutter users. Many of us actually engrave custom designs, such as text or patterns, on our everyday belongings to customize them. With SensiCut, we can take this one step further and engrave objects that consist of different materials across its surface. This phone case looks as if it had leather and wooden parts on its surface, but actually the wood-look part is made out of rubber, which doesn't look obvious in the camera image, right? To detect these materials, we select Scan Multi-Material Objects this time, and in this mode, SensiCut automatically samples points along the shape's outline and captures the speckle patterns at these points. So once complete, the UI automatically partitions the shapes into material-specific paths and assigns them the correct laser settings. And here's the final result. The quality is not great, but you can see it better perhaps on Zoom. So now that we know how SensiCut helps users in different ways, let's talk about how we trained the machine learning model, which can differentiate between 30 materials. To capture the samples for our data set, we wrote a script to automate the laser cutter's movement and image capture, which you see here in action. In total, we captured more than 38,000 images And we evaluated the accuracy for 30 materials, and this confusion matrix shows the results. Across 59 sample sheets from the 30 subtypes, we found that the average identification accuracy was 98.01%. So that was SensiCut as an example of natural tags. If you're interested in the technical details, we can chat more. And next, I want to talk about engineered tags, actually. And these enable us to define the type of information or pattern we want to embed on an object during the fabrication process itself. As an example, I'd like to talk about a project from Kite 2020 called GID. Here, we presented a new approach for identifying 3D prints using slicing parameters. And let me explain that. So in this project, our motivation was to integrate tags into 3D objects that users create using personal fabrication tools such as 3D printers. So to achieve this, previous projects suggested carving or adding visual 2D tags onto the surface of the object, such as this QR code or this linear barcode or a more customized pattern. As you see, all of these objects are visible and all of these tags are visible, and they dramatically impact the look of the object. So researchers then came up with new techniques to hide these tags. For example, Air Code uses a camera and projector setup to detect gaps beneath the object surface. InfraredTags use a terahertz scanner to detect even deeper holes. And Layer Code uses a modified SLA printer and customized resins to create hidden barcodes. As you see, these methods require the use of either specialized or high-cost equipment. And with GID, our goal was to have unobtrusive tags that are easy to fabricate and that can be detected using low-cost scanning tools. And the thing is, we actually do not create these tags. They're already there. GID uses the patterns that are already created by the regular 3D printing process. As you see here, when you 3D print an object, it inherently has distinct features due to the path the printer lays down. And if we have multiple copies that each have a different path layout, as you see here, we can distinguish them. Now let's talk about what determines how these lines are printed. Before a model is sent to a 3D printer, the user has to convert it into machine instructions, which is called the G-code file. This process called slicing is done by a software tool called Slicer. The Slicer software takes as input various parameters, such as the line angle and width, and outputs the G-code file for the printer. Now, if we manipulate these parameters for each of the copies we want to have, they will each have a unique surface texture, as you see on the right-hand side. And now let me talk about the GID pipeline consisting of 2 steps. So we will use an example where we will create a set of 40 key covers, unique key covers for our research group. And this is based on a real story. At the end of the semester, when lab members depart, we often forget to write down who has returned their keys, especially like the undergrads. So using GID, we can quickly identify whom the previously returned keys belong to. And the first step, tagging. So first we load the 3D model of the key cover, and then we enter how many instances we want, 40 in this case, and then click generate previews, which slices each instance with a unique set of slicing settings. And here you see the differences in slicing settings. For example, in the line angles, 50 degrees versus 5 degrees versus 20 degrees. And we can now enter a label in the form of a text, a URL, or an image. Since we want to give each key cover the name of one of our lab members, we just enter their names. And finally, upon exporting, each instance's G-code file is saved, as well as a dictionary file which stores these labels. We can now send the G-code files to our printer, and finally, the second step, which is identification. Here you see, although the printed keys look the same at first glance, they are actually different. So what we do is that we first launch the GID mobile app that we created and select the model we would like to scan from the library. The app then helps us align the camera image with the object by showing the target and the detected outline, similar to how check caching or document scanning apps work. And so when the outlines are aligned in this human-in-the-loop setting, the app automatically captures and processes the image, and after identifying the texture, it retrieves the assigned label and shows it on the screen. We check off the lab members who have returned their keys and send a reminder to everyone else. In the previous scenario, we talked about how we can detect textures on the surface, but we can also sense the interior of objects by adding a small light source. So this works because of the translucent nature of regular PLA filaments. If you're familiar, you can basically just shine light to reveal their infill. And here you see some different infill patterns. So for this type of detection, we use a stationary setup with an integrated light source. As you see, we have mugs that have different infill patterns on the interior, so we can actually detect that using image processing. So now one important question you might be wondering is how many instances can we possibly distinguish between using this technique? And here are the results briefly. We can have 204 using a camera and more than 17,000 instances if you use both a camera and a light. And to come to these results, we answered these two sub-questions. First, which 3D printing parameters can we manipulate at all? And second, per parameter, how many variations can we detect with a phone camera? Here's an overview of the parameters, and I'm not going to go into the details today, but happy to talk more. And our project page on our website also has a lot of details. Now, I'd like to introduce two of our applications. First, user identification. In this example, we have 3D printed mugs that each have a different infill, which this coffee maker can detect using a camera and a light source. After recognizing the mug and identifying its owner, it pours their favorite drink. So this is like a fun one. GID can also be used for finding previously used print settings, and this is especially useful when users want to replicate existing 3D prints, because oftentimes we try various printing settings to see which one works best for a given model, and then we just forget. So in this case, one of these 3D prints has the best mechanical integrity, and the user wants to identify its slicing parameters. Rather than carefully writing down which settings were used for which one, the maker can retrieve this information just by taking a picture using our application. Yeah. So that was GID, which is great for distinguishing between different copies of objects. However, one limitation is that the objects don't carry any data. So we, as users, are enabled to embed custom information. So the third project I'll be talking about today is InfraredTags, and it aims to overcome this limitation. InfraredTags are invisible markers embedded into objects that are 3D printed with an infrared transmitting material. Even though you cannot see these tags with the naked eye, they can be captured by using an infrared camera and computer vision techniques. So in this project, our goal was to create invisible tags that carry information that can be fabricated with common printers and detected rapidly using low-cost cameras. InfraredTags achieves this by using an affordable region of the electromagnetic spectrum, the near-infrared region, and let me explain what I mean by affordable. Here you see the electromagnetic spectrum, and here's a section of it. On the left side, we see the visible region, and on the right, we have different regions of infrared light. And because infrared light cannot be seen directly by humans, we can use these regions to encode and decode invisible information. Here you see some of the regions within infrared, from near infrared to terahertz. If you want to image objects in a long wavelength infrared or terahertz, that is going to be pricey. As you see in these examples, the longer the wavelength, the more expensive is the imaging equipment. However, near-infrared cameras are much more affordable, so they are particularly suitable for our purpose. And in this project, we used a $20 camera by Raspberry Pi. So that we know more about near-infrared, I would like to talk about how to actually embed infrared tags into 3D objects. So one key observation here is that many plastic materials actually pass near infrared light. Such materials are commonly found in TV remotes or other electronics. And for our goal, we had to find an infrared translucent 3D printable material. And after extensive testing, we decided on this filament by 3DK Berlin. And it's based on the most common 3D printing material, PLA, which means that it is very affordable and can be printed at regular temperatures. So we tested how this filament compares to regular PLA filaments and measured the transmission characteristics using the spectrophotometer. Here, the blue curve is for the IR PLA and the orange one is for the regular PLA, each for 1 millimeter samples. Let's have a closer look. On the x-axis, we have the wavelengths, including visible light and near infrared. The y-axis is the transmission percentage. For the regular PLA, we see that the transmission is at 0% for all wavelengths, which means that it blocks both visible and near infrared light. For the special IR PLA, we see that it transmits near infrared at 45%, which while it blocks most of visible light. Now that we know the material's characteristics, let me explain how the tag is actually embedded. Let's assume that this box is the original 3D model that we want to embed the tag in. First, we pick where the tag should go, should be facing, and then we go down the surface by a certain distance, the shell thickness. And underneath, we have the tag with the thickness value labeled as code thickness here. And the tag, which is a QR code in this example, is extruded as a cuboid. Now let me move this cuboid out of the object. You see how the main object on the right has a void where the tag can go in. And these tags are integrated and printed together. However, the tag is printed using regular PLA, and while the main object is printed with IR PLA. And this way the tag is detectable. Now you might be wondering what values should be used for these different thickness values. So to determine the shell thickness, we printed a sample pattern at checkerboard, and on top of it, we printed the infrared translucent PLA of varying thickness. Then we took a picture of it from above. This is how it looks to humans. Now, as you see, at a certain point, the pattern is no longer discernible, right? Well, the interesting thing is, when you image it with an IR camera, this is what you get. And when you run our image processing pipeline on the IR image, you're able to reconstruct the checkerboard pattern like this. And as you see, it gets worse with increasing thickness. So at a certain point, the pattern is no longer reliably binarized. And these two limits give us a range of possible values for the shell thickness. And for the sake of best detection, we use the smaller limit value for the prints. So now that we know how the method works, let's talk about the applications and the workflow. Infrared tags can be used to embed data about the object into the object itself, metadata. So in this example, we have embedded the mug's fabrication link. If the user likes the look of an object, they can take a picture of it to download its 3D model and print a copy for themselves. To embed this URL into the original object, makers can simply use our UI. And then you can directly 3D print the modified model. Here you see the print halfway through, which on the left you see the naked eye view, and on the right the IR view, which reveals the QR code. And for detecting the tag, the user can attach our infrared imaging module to their smartphones, and it consists of low-cost components, as shown here. And it is actually not necessary to use this module if you have a smartphone that comes with an IR camera, such as this one, OnePlus 8 Pro, which I brought with me. So if you're interested, I can show you some prototypes after the talk. And in our second application, I want to show you how infrared tags can be used to embed, to show device controls in augmented reality. So you see in the AR view, the user is able to identify the object and adjust the speaker volume, or set a temperature for this thermostat. Furthermore, infrared tags can enable multiple tags to be embedded in the same object. So in this example, the visible surfaces of the Wi-Fi router only have its network name embedded, whereas for safety reasons, the passcode is only embedded onto the bottom of the router, which allows the phone to automatically connect to it. So the final use case, you see how this plastic disc, which doesn't have any electronics in it, is used as a game controller. Even though the wheel is rotationally symmetric, the IR camera can see the fiducial marker inside and infer its orientation. As future work, we are also exploring the use of infrared tags for low-cost fabrication of motion capture variables. Here you see a passive bracelet with invisible markers. And here's a demo of the work in progress. The wearable tracking is used for creating a digital twin of the user in the virtual environment on the left side. And if you're interested, you can find the code for InfraredTags in a detailed tutorial on our GitHub repo. So that was InfraredTags as another example of engineered tags. So today I presented two types of tags, natural tags and as shown in SensiCut, and engineered tags as shown in GID and InfraredTags. And I also have a new work coming up soon, hopefully, called struct codes. It's another example for engineered tags. So struct codes, for example, augments this picture with narration, provides personal labels on these folders, helps update the status of this plant, like watering information, or links to online resources about this chair. So the way it works, it actually embeds unobtrusive codes by slightly adjusting laser cut structures such as finger joints, which you see here, and limbing hinges, which you see here. So to conclude, as I explained in the beginning, my bigger vision is to enable users to more unobtrusively identify objects, products, and materials in their surroundings so that they can access and retrieve information related to them quickly and seamlessly. And in the future, I'm planning to explore 4 different directions that you see here. The first one is for VR, which I already talked about a little bit. And secondly, when it comes to AR, I plan to integrate invisible tag sensing capabilities into new form factors such as smart glasses, which is helpful for creating personalized interfaces and seamless interfaces, like the example I gave you in the beginning, the grocery store, where your smart glasses can discreetly sort through all the products and pick the best one that best suits your needs. Another application area I'm interested in is accessibility, specifically for users with visual impairments. So you can imagine a mug with like an embedded infrared tag informing a blind user that it's not microwave safe, or providing extra information on how or where to hold an intricate object, or embedding accessibility captions into documents that often get lost when a document is printed. Last but not least, I'm also very interested in the privacy aspect. We researchers and engineers use infrared sensors and other types of active sensing methods more and more in the systems we build, like the iPhone and the HoloLens. But like users are not aware of this because it's like invisible, right? So a research prototype we built recently is this wearable that warns the user when an infrared sensor like Face ID is detected in the environment and attempts to block it. And we want to explore this more in the future. So if any of these directions sound interesting to you, let me know after the talk and we can chat more. I'm always looking for more collaborators. And I also want to thank my previous collaborators and current mentors for their help. Thank you so much for your time, and I'm happy to answer your questions.